Hey guys, what's going on? So today I'm starting a playlist in tensor calculus, and this is going to be a growing playlist. And I've always wanted to do something like this, even though I'm skipping calculus 1, 2, and 3. I'm starting with calculus 4, which is tensor calculus, and is oftentimes one of the more difficult things for us as scientists and us as physicists and mathematicians to understand. That's one of the reasons I decided to do something like this sooner rather than later. Also, tensors have always been of interest to me. Ever since I heard about them, I've always wanted to learn more about them. And so this is this is going to be an ever expanding playlist as far as I can take it. But for right now, I want to start at the bare basics, and I am going to assume that you know a little bit of linear algebra um, and basic physics, and also basic calculus to go through this course. I'm going to assume that stuff. So this is tensor calculus. Tensor calculus. And in terms of prerequisites, so prereqs, in terms of prereqs, linear algebra is probably the most essential. Because I'm gonna try to go over calculus and stuff like that in this playlist, but calculus obviously is up on the list as being a prereq too. Calculus 1, 2, and 3. If you have an understanding in those, this playlist will come easy to you. But again, I'm not requiring that you know all three of them. I'm just saying that if you've had exposure to this kind of stuff already, it'll make learning tensor calculus a little bit easier. The differential equations, not so much. These are probably the two math courses that are going to be most helpful. If you understand these courses, then you're going to have no time understanding this tensor calculus playlist. So let's get right into this. So as I alluded to in the title of this, this is a justification for the existence of covectors. So I'm jumping right into covectors. I'm not even talking about vectors. And part of that is me, again, believing that you've taken at least some basic physics. And basic physics, again, would be one of these prereqs. Physics. Okay. Again, this all these would be not necessary prereqs. I think the one necessary one would be linear algebra. So we understand the concept of a vector. Okay, so a vector is something that has a direction and a magnitude. So we have a vector. Vectors have direction and magnitude. Direction and magnitude. What about a covector? So I'm jumping right into here, right into this on covectors. And I'm going to illustrate this with an example. So imagine we have a block. Imagine we have a block on a surface, okay? And this block is moving. It's being pulled, perhaps, by one of us. And it is being pulled with a certain force. And so we know that the force of an object is mass times acceleration. So if I am pulling this block such that its acceleration is equal to 1 meter per second squared, and say its mass is equal to 5 kilograms, well then the force is just mass times acceleration, so that's going to be 5. It's 5 newtons. So therefore the force is equal to 5, I can rewrite that, 5 newtons. Okay, and the acceleration, so this is a case 1. So case 2 would be, okay, suppose I am now pulling this block with an acceleration such that it is in centimeters per second. Okay. So if this is in centimeters per second, the mass doesn't change. Therefore, the force is going to equal, well, we know that 1 centimeter is the same thing as 0.01 meters. Okay, so that's going to say that the force is 0.05 newtons. Okay. So this is the force case. So we're considering a force. Okay. Now let's consider another object. And the other object is, as we've learned here from basic physics, if you haven't taken physics yet, it's okay. However, this equation that I'm going to put at you might come out from nowhere. But believe me on this. Suppose we have a capacitor, okay? So we have this is our force scenario. So I'm going to underline that force right there. Now we have a capacitor. Okay. Now this capacitor, in this capacitor we have, so here's one end of the capacitor, here's the other end of the capacitor. In this capacitor we have an electric field. Okay. Now the equation for an electric field inside this capacitor is E, I'll put it over here, E equals the voltage divided by the distance. So the voltage across this capacitor divided by the distance across the capacitor, the distance between the two plates, the two capacitor plates. These are two capacitor plates, make that a little clearer. So that's D. So the voltage across these, applied across these plates divided by the distance is going to give us the component of the, this is the electric field. Okay. Now you could see if I decrease, if I start with meters, okay, I can get a value for E. If I decrease down to centimeters, my E is not going to decrease. Since I'm decreasing the denominator, the value for E is going to increase. So you can sort of think of it as you're squeezing the two plates together, there's going to be a stronger force. There's going to be a stronger electromagnetic force in there, and the value of the electric field is going to increase. Okay, so the electric field is an entity that increases as you decrease your basis. Because we went from meters to centimeters, but the electric field increases. Oppositely, the force is an object. A force is a mathematical or physical object that increases as you, that decreases as you decrease your basis. Okay, so decrease basis for the force, then the force decrease basis for the electric field, then it increases. So this thing oppositely transforms with the basis, this object here. This object here, the force can be represented as a vector, so the force is a vector. decreases as your basis decreases. So we call one covariant. This is the covariant case. Covariant case. And this is the contravariant case. Like that. So we could see now what's an interesting equation though. So to bring this home, suppose we have E is, well, we know, so that we have this equation here that we get from general physics. E equals F divided by Q. Where the Q is some charge, and then emanating from the charge is an electric field. All right, and as we decrease, or as we increase the distance, again, the electric field slowly decreases from this charge. As the smaller arrows means that it's decreasing as the distance is increasing. Right? So again, you have this object that decreases as you increase the distance. Again, this is a contravariant object. But again, we have this force here. This force is a covariant object. If I rearrange this equation, so we have a covariant object inside an equation for a contravariant object. That seems to suggest that Q, if we rearrange this equation, is equal to the force divided by the electric field. So when we apply a covariant object with a contravariant object, it doesn't have to necessarily be in this division-like way, but when one is applied to the other, we get Q, and Q is neither a vector nor a scalar. Okay, it's not a vector nor a covector. It's a scalar. Q is a scalar. So a contravariant component, or a contravariant object, applied to a covariant object will give us a scalar. Okay? I want to move on now to formalize this in some math terms. All right, so we said that some covariant object applied to a contravariant object gives us an invariant object. All right, so this is interesting, okay? Now, what is a contravariant object? Well, back here, I said the contravariant object was the standard vector that we always see in physics and math, okay? So this contravariant object is a vector, and a vector can be represented as a column vector, where its components are right here. Suppose this is a two-component vector in a two-dimensional plane. Okay, it has in the x direction, it has a components, or its component is a. In the b direction, its component is b. Okay, what about this covariant object? How can we represent that thing? Well, we represent that thing as a row object. So one thing is a column object, the other thing is a row object, and say this has components C and D. Okay. Now we would do this, now we would perform this much like we're performing matrix multiplication. Even though this row thing isn't really a matrix, we could still perform some sort of matrix multiplication, and we get AC minus, or AC plus BD. BD, like that. Now this is a scalar, right? So a covariant object can have components now. Covariant components are organized in this row-like fashion. Contravariant components are organized in this column-like fashion, like we typically see a vector. And then we get a single component object, which is an invariant. So suppose now that we want to be able to visualize this. How can we visualize something like this? Well, again, here's a vector. Here's a vector. And say we have lines passing through this vector. Now this is not the base. I'm not drawing a Cartesian coordinate system. This object is oriented. What I'm doing is I'm creating an object that's oriented in this horizontal direction. It's going this way, and it has planes. These are like planes. You could think of these as planes almost, to maybe not confuse ourselves with these are planes, to not confuse ourselves with a coordinate axis. Okay, this thing has components. This whole thing is an object, and it has components. In the x direction, it has c components, or it's in the x direction, it's the coefficient in front of the basis is c, and in the d direction, maybe they're oriented vertically. These things are oriented vertically. Okay, so we might have something like this. Might have something like that. Okay, now suppose this arrow goes all the way out to here, actually. Okay, the scalar comes from we want to ask ourselves how many of these objects, these horizontal objects, does this arrow go through, and how many of the vertical objects does this arrow go through? Well, it goes through 7 vertical or horizontal objects, and it goes through 3 vertical oriented objects. Okay, and that's how we get scalars out of this. Okay, so when these planes are applied to a vector, we can get scalars out of them. So in this direction, the scalar we get is 7, because, or not 7, that's not 7, that is, let's count that. That would be 1, 2, 3, 4, 5. And going in this direction, the scalar we get is 1, 2, 3. Now this is a very rudimentary way of understanding how a covariant object and a contravariant object can be applied to one another. I would avoid thinking of them like this, but again, if you really, really want to conceptualize and tangibilize this in your head, you can think of these things as planes with components to them. Okay. This is just a suggestion, though. I would not recommend viewing them like this, because once we get into tensors, visually seeing these things in your head is going to be really hard and probably not worth it. So that's all I want to go through here. Again, my lectures for this tensor calculus course are going to be a little bit longer than my general courses. I have a course going on general chemistry right now as well. And I intend to make more courses on physics, biology, structural biology. I'm in cryo-electron microscopy, and I intend to come out with courses in those as well. If you like the way I teach, please go to my website at tristancarmacy.com. If you're interested in any private tutoring, you can go to my website as well and check that out if that's something you're interested in. hit that subscribe button if you want to, and I will see you in the next one. Thanks for watching.